And then second, do you remember, it feels like a long time ago now, but there was a problem, one of the heat problems. It had to do with the total, I guess it was the total value of Q for, God, I don't even remember what it was. It was an object in the atmosphere. And there was radiation. Not that one, but there was another one, I think. It was the grill. Yeah, the grill hood problem. And there was this question. So you had to use radiation and convection. And I wasn't sure whether the hood would get radiation or significant radiation from the atmosphere. But yeah, you do have to include the radiation coming in. So it will get significant energy as radiation from the surroundings. And so you have to use that formula that's like Q dot is equal to the emissivity times the constant times the area times the quantity, T, I guess body to the fourth minus T surroundings to the fourth. When I did it in class, I just did it as heat being emitted by the hood, but that was wrong. Anybody have any homework questions? I guess we just took the test, so I'm thinking probably not. Or anything that came up to you about occurred to you about the test since you took it? Mm-hmm. I don't remember it at all. Let's see. Okay, so on the last one, so Q is, heat is, energy is leaving the gas into the surroundings. And what are we looking for? So yeah, that's right. Q would be negative because Q is positive if heat is going into your system, and W is positive if energy is leaving your system through work, like it does in a heat engine if your system is the gas in a heat engine. What happens here? Is it steady state? Yes. So if W is if Q is negative, then W has to be negative, or if Q dot is negative, W dot has to be negative. Yeah. The surroundings. Energy is transferred from the gas. Blah blah blah. Yeah, so if energy is just leaving at 0.2 kilowatts through heat, then work is being done at that same rate of 0.2 kilowatts. Yeah, work is being done, so W is negative, yeah. Any other questions about it? I don't know. It was the first test I wrote in a few months, and there were the units issues we caught, and then worse than that, there was a question that was worded, used a funny word, and I know at least I saw one person who got screwed up by it. Where was it? Yes, wood downward force wood, and so number 2. Yeah, wood downward force wood. That's not good English. And what I wanted was what downward force F would be required, but I know I saw at least one person interpret that as would a downward force be required, and then just answered yes. So that's accurate, so good job on that. But well, I think what I'm going to do on that is I'll think about it more. I've sort of thought of it like walking around, like, oh, what am I going to do about it? But I think what I'll do is, if anybody didn't do the thing I was planning for you to do, I'll just do it as if they took a test that had that many fewer points. I'll just wipe it, because that's not really an equivalent difficulty of question. You know what I mean? Yeah. Yeah, right. But so you won't get penalized for it anyways, because it's my bad. Yeah. Yeah. Okay, so that's it for the test. It'll be back on Tuesday or face kick. My face? So you can practice a picture of my face. Well, it will. Yeah, if anyone has like Gene Simmons boots, that would be cool. But it will be. I don't know what time, but it'll be up on D2L sometime before I give it back to you, because that's what I keep grades in. So. All right. Yeah. Okay. Let's talk about that one. Okay. Anybody have the homework problems? Thank you. So air is contained in a piston cylinder. The piston's connected to a spring. The volume inside the cylinder changes slowly. It says here, I put quasi-equilibrium in parentheses, but anytime a problem says something about changing slowly, that's telling you that you can make that quasi-equilibrium assumption. Okay, because there's no like inertial effects that are messing up relationships between the properties. So the volume is decreasing, and the spring force is decreasing. Okay, so you got the area of the piston, the atmospheric pressure, and so we're going to draw a free body diagram of the piston, and then we're going to use the fact that that we have a linear force to determine what the pressure is as a function of volume, and then we'll use pressure as a function of volume to calculate the work. So if you're trying to calculate W based on pressure and volume, you know you're going to have to integrate PdV, and so what you want is the pressure as a function of volume. Okay, so let's see what we got. So a linear spring means this, right? The force is equal to K delta X. But notice that if you're applying a force to the top of a piston, the volume is also linear with that delta X of the piston because the cross-sectional area isn't changing. So, you know, we can also think of this as, I'll call this one K1, then K delta V. And so a free body diagram of the piston. We have the force coming down from the spring. I'll call that F sub S. And we have an atmospheric pressure of 100 kilopascals times the cross-sectional area. So 1, 2, 3, 4, 5. So I think that's so the atmospheric pressure is 1800. And then the only force applied from the bottom is the pressure in the gas times that area of the face. And so we know that, you know, Newton's second law says 0.18 times the pressure has to be balanced by 1800 plus F sub S. And now we can say 0.018. Yes. Okay, so now the thing is we know, so what we're trying to head for is calculating the pressure as a function of volume. What's the first thing we're supposed to do? Calculate the pressure. So it's all just trying to find. It's all just trying to find the pressure as a function of volume. We know that that spring force is a function of volume, and so once we find what the function representing that spring force, then we can calculate P. So let's say yeah. Yep, that's what I'm going to do. Yeah. So the force of the spring is 900, which is equal to so let me take a step before this. So the force of the spring as a function of volume is this. It's a linear function. And so the force of the spring at a volume of 0.003 is 0.003 V plus B, and that equals 900. And the force applied by the spring at 0.002 is 0.002 times V plus B, and that's 0. And now we have a system of two equations for two variables. So B is equal to negative 0.002 V. Plug that into the first equation. You get 0.003 V minus 0.002 V is equal to 900. So, wait, I'm not trying to solve for V. That should be A. Yeah. So these are A's. So 900, 9,900. So A is equal to 9 times 10 to the 6, right? And then B is equal to negative 0.002 times 9 times 10 to the 6. So that's 18 times 10 to the 6, 0.8. What's a factor of 10? Okay, so this is to the 5th. And then we get for B. $1,800 negative. Okay. Okay, so the spring force as a function of volume is 9 times 10 to the 5th times the volume minus 1,800. Now we can plug that into Newton's second law. So 0.018 P is equal to 1,800 plus 9 times 10 to the 5th times the volume minus 1,800. And so that's just 9 times 10 to the 5th times the volume. And so P is divide by 0.018. Someone calculate that for me. 5 times 10 to the 7 times the volume. And so that function gives you, if all we were trying to do was find the pressure at the two endpoints, it would have been easier than that. But now you can solve part A with that function, and then for part B, W is just equal to the integral from 0.003 to 0.002 of 5 times 10 to the 7 V dV. Any questions about that one?
Pushing down at point 1, and then made that the pressure pushing out at that point.
Right.
And then I just set the spring force to 0, calculated it again, so I think 150 pascals at point 1, 100 at point 2.
Yep.
And then just did it off of that, did a linear function.
Just fit a linear function to it.
Yeah,
that makes sense. Yeah. I don't know. I mean, I think I tend to approach these problems whenever possible, just like it's a linear function, like This is the definition of linear function. Now that's two equations for two variables. You know, that's what my voice sounds like while I'm doing it. Say that again. Oh yeah, right. No, you can't. So really the next thing we're getting into is, you know, that just all has to do with the relationships between properties of substances. And for certain gases, the relationship between pressure and volume at a fixed temperature is, you know, PV to some power is equal to a constant. But without knowing any more about the material, we definitely can't make those assumptions. Well, so the volume decreased and the pressure decreased because this thing was losing energy through heat, you know. So energy was being added by compressing it, but more than that energy was being removed from heat, and that just never came up in the problem. Mm-hmm.
Okay. How did we end up in that solution there with pressure being a positive function of volume? If pressure, hang on a second, the pressure decreases as the volume. Wait, yeah, no, never mind. That makes sense.
Okay.
Yeah. Never mind.
Any other questions about this one? Any other homework questions? Thanks. Okay, so it's been a while since we talked about new stuff, but the last thing that we were talking about was using, so last time, using the differential form of the first law. So first of all, that says dE dt is equal to Q dot minus W dot. And we talked about using that for steady state processes. So in a steady state process, all properties are constant. So dE dt is equal to 0. And you get a form of the first law that looks like 0 is equal to Q dot minus W dot. And then, you know, that goes pretty naturally with the different calculations of the heat, you know, the different types of heat. So you can go through, you know, calculate the net radiation or conduction or whatever, and use that to calculate the power. You can also, so that's one time that it's useful to use that differential form, but you can also use that differential form for transient processes that aren't steady state, if you know some, one of the functions that defines how it's changing. So you can also use this differential form for transient processes. Transient is just not steady state. So I'm just going to do an example. So let's say that the rate of heat that's added to the system is Q dot equal to 200 times the quantity 1 minus e to the negative 0.05 t. Where the system is an electric motor, and rate of heat added to, no, that would have to be heat lost then. So this is, so we can think of this as the rate of emitted energy. And that expression represents heat dissipation. And then some other stuff goes on with this motor. It's electric, so it has to be getting power through electricity. So the input power, bless you, is 2 kilowatts. And it's a motor, which means, it's causing a shaft to spin. And so it's causing a shaft to rotate at 100 radians per second. With a constant torque. M for moment of 18 kilowatts. That's a moment, so it's not right. That moment should be in Newton meters. Okay, so the question is, what's the change in energy of the motor over time? And since this motor isn't changing speeds and its potential energy isn't changing, this is just a change in internal energy. Yep. That one formula I gave you is heat leaving the system. Rate of, yes, that I was thinking about it wrong when I wrote that. It is removed. Okay, so we're going to use this equation that says du dt is equal to q dot minus w dot. For q dot to be positive, that has to be heat added to the system. This is lost from the system, so q dot is negative q emitted, so that's negative 200 times the quantity 1 minus e 0.05 t. The work done by the motor is so W dot to be positive, the motor has to do work. Work is being done to the motor by the electricity. That's energy that the motor is gaining. And the motor is doing work on its surroundings through that moment and that angular velocity. So this is going to be equal to 100 times 18. That's the work that it's doing on its surroundings. Minus, where was the 2? So minus the work that's done on the motor by the electricity. And so we get a value delta W of negative 200. Any questions about that setup? So much of it is just getting the directions of flow right,
About 2,000 was the electricity.
Yeah, 2 kilowatts was how I said it, I think. So 2,000 watts. And so now we can put it into the first law. It says du dt is equal to negative 200 times the quantity 1 minus e to the negative 0.05 t minus negative 200. And so the 200s cancel, and you just get e to the negative 0.05 t.
Once you distribute
Yeah, so we have a negative 200 times 1 here, double negative here. Yeah, you're right. Yes, that does not cancel. Positive. Any questions about that? And then the last thing I want to say before we go on to sort of a new topic is just really briefly, I want to mention this idea of cycles. It's going to end up being a big thing. So a cycle is something that, so you can think of it as not as strong a statement as steady state. It's sort of the same idea. Steady state means that all properties are constant at any two instants. They don't change at all. cycles, the properties can change, but at the beginning and end of the cycle, those properties have to match. Okay. So all the properties return to the starting values. And so in a cycle, if all the properties return to the starting values, the standard form of the first law, so we have the change in energy is equal to Q minus W over the cycle. This is 0. And so 0 is equal to Q minus W over the whole cycle. Heat pumps and engines and refrigeration, those are all cycles. So we're going to use that idea. And for now, I just want to point out the similarity between this and steady state. It's not the same thing. This is just saying this is true if you're looking over between two specific instances. If you look at two different instances, that won't be true. So it's similar, but not the same as steady state. So now we're going on to a new topic. Properties of simple compressible substances. Okay, so with Newton's first law, with the first law of thermodynamics, we have this relationship between change in energy and heat and work. Now what we'd like to be able to do, and we were talking about this earlier, can we, you look at this stuff and you wonder, you see some problems where the pressure times the volume to the 1.3 power is a constant, and you'd like to know, is that something I can use all the time, or is that something I can use in this problem or that problem, and how do you know? Those are relationships between properties that have to do with just the materials themselves. And if we can come up with good relationships, ideally if we can come up with, say, calculating the pressure of this substance as a function of the volume and the temperature or something, then that's another constraint that we have to let us solve for things that we don't have, we're not given in the problem. So that's what this is about. You can think of, so we're looking for relationships between properties. And if the material is a simple compressible substance, means that it's homogeneous, the same composition everywhere, and doesn't depend on electric fields or magnetic fields. There's no magnetic or electrical interactions in the substance. So electrical. And what, well, as long as you don't apply, because of the magnetic field, as long as there's nothing around it causing a magnetic field, that would still be fine. You know what I mean? And I say homogeneous, but that doesn't mean it has to be a single, a single chemical. Like air is a simple compressible substance, even though it's made up of a bunch of different chemicals. It's homogeneous because if you go over here, it has the same makeup as if you go over to this side of the room. And the thing about simple compressible substances is then, so if you're dealing with a simple compressible substance, all properties at a state can be specified by just two other properties. The properties that we're going to be, well, so to make sense out of that, think of the ideal gas law. PV equals nRT. The properties are pressure, volume, and temperature. And this equation says if you know two of those, you can solve for the other one. Okay. Well, it gets a little more complicated than that because a little more complicated because simple compressible substances can change phases, but that's the idea. And so here's what we know for all simple compressible substances. In the single phase regions, you can write pressure as a function of the volume and the temperature. And the volume that we're going to be talking about here is the specific volume. So that's the volume per mass. And the volume, the specific volume, can be expressed as a function of pressure and temperature. And the temperature can be expressed as a function of the pressure and the specific volume. In the phase change regions, temperature and pressure are dependent. And so you can write the pressure as a function of specific volume and temperature, and you can write the temperature as a function of pressure and specific volume, but not the specific volume. That's it. Any questions about any of that? The relationships between pressure, specific volume, and temperature can be represented by a 3D surface. In pressure, specific volume, temperature, space. And it's sort of a crazy looking thing. Have you seen the PVT surface before, like in physics? Okay, so I'm going to put it in the notes here. You can see what it looks like, but mainly what we're going to use are two-dimensional projections of this surface because it's sort of hard to wrap your head around a 3D thing. At some point, I'd really like to do a 3D print of it, you know, if I can find like an equation where, so you can sort of hold it and turn it around. But anyways, here we go. Okay, so this is, yeah, I mean, if you're really good at picturing stuff in 3D, then that tells you everything you need to know about the relationships. And all you would need for one material or another is you would need to know the value of this critical state. You would need to know where this triple state is, and then you could sort of fit this thing to. This is called PVT surface. Or the PVT diagram. Of a material that contracts when it freezes. Okay, so most materials contract when they freeze. I think all metals do that I know of. The main counterexample is water. When water freezes, you know, it expands. That's why you leave wine in the freezer too long, it explodes. And so I'm going to put up another one of these that represents materials that expand when they freeze. It's mainly important because water is such an important material. But the difference is whether, so if you're going down this face here, if the material contracts when it freezes, It goes in here and then pops out towards a higher volume as the temperature goes up, because then you're melting.
It would only ever expand when it freezes due to some weird anomaly in the crystal structure.
I really don't know about that, but waters has something to do with that. That's definitely outside of my area of knowledge, but mhm. Yeah, right, exactly. Yeah, that's right. So this is one for a material that expands when it freezes. So this one represents most things, definitely metals. This represents water, and you can make sense out of what's going on here. So if you're going to a higher temperature, you're going from frozen to melted, and you have a certain specific volume, and then it melts, and your volume decreases. But that's the only qualitative difference between those, and that's not really, that part of the PVT diagram is not going to matter to us. So that's the good news. Yeah, exactly. Yeah. So the good news is what happens when a material freezes is not going to be important in this class. And the reason for that, I'll go into it in a little more detail in a few minutes, but we are going to be totally concerned with liquids and gases, and that's all. We don't care about solids. I mean, you can imagine, like, you've never heard of a cylinder and a piston setup where the thing turns into a solid, because it's not useful. I'll talk about why that is. I'll say vapors. The main feature that the sort of trickiest feature for us that comes from that PVT surface is called the vapor dome. Okay, so both of these have it. You can see it a little more clearly here, but this thing that goes up like that is called the vapor dome. And for any of any point on this surface represents a state, material in a certain state, And any of the states inside this dome are mixtures of liquid and gas. And those mixtures of liquid and gas are going to be really important in thermodynamics. So I'm going to just draw this shape. So inside the dome is a mix of vapor and liquid. At its bottom edge is something called the triple line. At the top is called the critical point. And the side to the left of the critical point represents a saturated liquid. I'll define these terms. And on the right side is called a saturated vapor. So the triple line, yes, yeah. Yeah.
So when you say that it's a mixture of vapor and liquids, does that mean that if you allow any amount of the sample to equilibrate at that temperature, or to be uniformly that temperature, I should say, there'll still be such a mixture? Like it'll just be some amount of vapor?
Yeah, it's an equilibrium there in a mixture. Yep. No, I don't think any of this is obvious. Okay, so the triple line, first of all, that is, that line represents all the states where vapor, liquid, and solid exist in equilibrium. So at those combinations of pressure, temperature, and volume, you could have an ice cube sitting in a puddle and steam, liquid, gas, all in equilibrium, and they won't be moving in one way or the other. The critical point represents a temperature and pressure above which there's no distinction between gas and liquid. So if you get above that temperature or above that pressure, the material, the phase is called supercritical fluid. It's not a vapor, it's not a liquid. Be careful because it might be hot. And then saturated means at the temperature and pressure of phase change. So at atmospheric pressure, liquid water at 32 degrees Fahrenheit is a saturated liquid. And solid ice at 32 degrees is a saturated solid. It means if you, whichever, so like for liquid water at 32 degrees, if you increase its internal energy at all from there, it's going to start to, it's like it's ready. It'll start to, well, sorry, I said it the wrong way. If you pull internal energy out of it for 32 degree water, it'll start to freeze. So a saturated liquid is liquid at the boiling point. And a saturated vapor is vapor at the condensing point. And you might think, with all the complications that we're going to see coming up due to phase change in the math, you might think, like, wouldn't it be easier to just avoid saturated states and just stay, like, what if we just kept everything gas, and why not do that? But we'll see that for the specific things that we're trying to do, those three things that I keep talking about, engines and heat pumps and refrigeration systems, I'm going to try to point out that actually using the phase change between liquid and gas gives a lot of power. It's a big part of getting these things to work efficiently. And so saturated liquids and saturated vapors are going to come up all the time. Yep. Yes, that's right. We're not. That's right. Yep. Yes. Yes. Yep. So if you took any more internal energy out of it, so if you gave any energy away through heat, that would show up in turning into a liquid. Yep. So yeah, you'd have all gas, all vapor. You'd take a little energy out, and then you'd have a lot of vapor and a little liquid. Take some more out, you'd have more liquid, less vapor, until it's all liquid. Okay, so the next thing we have to talk about is some of these projections. It's easier to deal with 2D projections than to deal with that three-dimensional surface. And so there are going to be three 2D projections, and they'll all be useful for different things. The first one is called phase diagram. That's a pressure versus temperature graph. The second one is going to be a pressure specific volume diagram. And then the third one that we're going to use the most today and Tuesday is a temperature specific volume diagram. And so here's the idea of these projections. So there are some difference, this only shows two of them, but you can do projections of any two of those dimensions onto a plane. So if we do the projection where we're not looking at the volume, so we're looking at a plot of pressure and temperature, you get this thing. That's the phase diagram. That's the first thing we're going to talk about. And notice the phase diagram is different from the other two in that the phase diagram is not, we're not going to look at this in terms of like slices at different specific volumes. All the other ones we're going to look at at different lines that represent different values of the property that's not shown. But this one, we're not going to do that. And then if you switch to this other dimension where you're not looking at the temperature, you have pressure, vertical, volume, horizontal, and you get the pressure volume diagram, and there you can see the vapor dome.
They're called bubble curves, right?
What?
Formulating for them are control lines.
They like mathematically, yes, but in this they call it like, so this one, for example, all these lines you see represent what happens at if you hold different temperatures constant while you're changing those values. And so like these are called isotherms because you keep the temperature iso. Okay, so the first one is the phase diagram. That has pressure on the vertical axis, temperature on the horizontal axis. And there are two of these depending on whether the material expands or contracts on freezing. Again, that's not going to matter for our calculations, but let's see. I got these somewhere. Phase diagrams. So if you have a material that when it freezes, it contracts, the line between solid state and liquid state angles off to the right. And for water and the other, handful of materials that expand when they freeze, the line between solid and liquid heads off to the left. But we're not going to be interested in that region. We're going to be interested in the region over here, and those look the same. And on any one of those red lines, you have a material that's between phases. Some is one phase and some is the other one. So on the red lines, the materials are a combination of the two phases. STR, triple. Okay, so yeah, I'll talk about that in a second. Materials are a combination of the two phases. Okay, and so remember up when we looked at the crazy thing, there was that triple state line where all of those states are states where liquid, solid, and vapor are in equilibrium. When you project it onto the pressure temperature plane, those show up as points. And so this and this are called the triple point. Any other questions about making sense out of that? I don't have anything else to say about that one. Then the next one is the pressure specific volume diagram. This is the pressure, the PV diagram, the pressure specific volume diagram. So you have pressure on the vertical axis, the specific volume on the horizontal. This is the vapor dome. And so you can see over here, you have a saturated liquid. Over here, you have a saturated vapor. Here's the critical point. And these different lines that are shown, the dotted lines, those are the isotherms. So for lower temperature, if you have a specific, so what those are, isotherms, pressure volume. So if you have a low temperature, then the relationship as energy is added or removed follows this. If you have a higher temperature, this. If you have a temperature that's higher than the critical point, you get an isotherm that looks like this. It never gets into the vapor dome. So that's for a T that's bigger than the critical temperature. Any questions about that? And I don't have much to say about this yet, and we'll talk about phase change and start getting into the math of it on Tuesday. But let me just put the TV diagram up here. So the temperature specific volume diagram. Okay. So now these lines represent constant pressures. This one is really nice, I think, for me. This one makes a lot of sense for thinking about phase change, because this is the way you think of a phase change, holding the pressure constant and increasing or decreasing the temperature. So this is really easy to visualize what's going on. So the dotted lines are what happens if you hold pressure constant and increase or decrease the internal energy. And the only thing, well, you can see the same features as on the other one. On this side, it's a saturated liquid, saturated vapor. There's the critical point. But one thing you see is that if you hold the pressure constant and add energy, you get a very steep increase in temperature without much change in specific volume. Okay, this is specific volume. Okay, so when you're going from saturated liquid. Okay, yeah, so when you're going from, so over here is the liquid region. In the liquid region, I'm almost done. You're like, that's okay, I'm not writing anymore anyways. In the liquid region, increasing energy produces very small increases in specific volumes. And so if you think about like what you're trying to do with a heat engine, you need a big increase in volume so that you can do work. As you get into the vapor dome, you get big increases in specific volume. And in fact, you know, in the vapor dome, the temperature stays constant as you add energy. It's sort of a weird thing, but that's what happens with phase change. Okay, so while the temperature stays constant. Okay, that's all. Have a good weekend.